Hi, Mr. Spone here, bringing you another Student Tears Productions. This time we're going to talk about our separating of a mixture lab and how to do the calculations. So in lab you were given a mixture of sand, salt, and iron, and I asked you to use the physical properties of each component to separate them and determine the percent composition by mass. So to get the iron out of the sand and salt, it was pretty straightforward. You just used a magnet and recorded the mass before and after so you could figure out how much iron you had. And in that case, we were then left with just sand and salt. So how do we separate sand and salt? Well, we know that salt is water soluble and sand is not. So we basically used a wash bottle to pour some distilled water into our sand and salt mixture. And with the salt dissolved, and we were able to simply decant off the salt water. And we did that multiple times to make sure we removed all of the salt, or at least the majority of the salt, to reduce our error. So we simply used magnetism to remove the iron filings, and we used solubility to get the sand from the salt through decantation. And then we were left with, of course, sand and water and salt and water. So we added a whole nother substance to our mixture, but it's really easy to remove water from sand or salt. All we did was heat it up, boiled it to constant mass, and evaporated all the water away. So we basically just kept heating each solution separately. I shouldn't say solution for that one, but we heated each separately and removed all the water, and we were able to get the mass afterwards. So we ended up with some data on this next page that looked a little bit like this. So you had to do some calculations with this, and this is kind of probably why you're here. So you had the data: mass of the evaporating dish, mass of the sand and evaporating dish at the first heating, second heating, and so on. So you have all these numbers, you followed your procedure, and now you're like, well, I got to do some calculations. If you're a little confused, this should help you out. So let's just jump right into it. How do we get the mass of the mixture from our data? Well, we had an empty evaporating dish, and we know the mass of it was 30.44 grams when it was empty. And then when we poured the mixture into it, the mass went up because now you have the mass of the evaporating dish and the mixture. So in order to get the mass of just the mixture, it's really just a simple getting a difference, doing a subtraction. So if we subtract the evaporating dish and mixture mass from the empty dish, the empty evaporating dish, we get the mass of the mixture. And that's pretty straightforward. So we subtract those two numbers, 32.94 minus 30.44, and we have a mass of the mixture of 2.50 grams. Just remember, in subtraction, sig fig rules, it's the number of decimals that matter. So both of these numbers have 4 sig figs, but each has only 2 decimals, and when you're adding or subtracting, you always gotta remember your decimal rule. So 2.50, that's our mass of mixture. We wrote that in. How do we figure out the mass of iron? Well, we again know that the evaporating dish and the mixture, we know the mass of that. It was 32.94 grams. And then we ran the magnet through and we took all the iron out. So the mass of this system decreased because we removed the iron out. And of course we determined the mass of it afterwards. What was the mass of the mixture of salt and sand with the iron removed? We did that. So we know that it was 31.82 grams. So again, we're just getting a difference. To figure out the mass of the iron, well, this is the mixture with the iron. This is the mixture with all the iron removed. So obviously the difference between these two has to be the mass of the iron. So subtract the two numbers, get a difference, you end up with 1.12 grams. Again, same sig fig rule, so that gives you the mass of the iron, 1.12 grams. Pause the video if you have to. I'm going to keep rolling through, and you can check your own data and figure out how to do it from there. So how do we get the percent iron by mass? And we're just simply calculating a percent. If you had a room filled with 10 people and 6 were boys and 4 were girls, well, 6 out of 10 are boys. That's 60%. You just divide the component part by the total multiplied by 100. That's just getting a percent. Pretty straightforward. So percent iron by mass is going to be equal to the mass of the iron, mass of only the iron, divided by the mass of the whole mixture. And we know the mass of the iron. We just calculated that, and we also know the mass of the mixture because we calculated that as well. So the mass of the iron is 1.12 grams divided by the mass of the mixture, which is 2.50 grams, and you multiply that by 100 to turn it into a percent, and you end up with 44.8%. So we put in the 44.8%. That's the percent iron by mass. Now we need to figure out the mass of the sand. Well, it's important to remember our procedure, which sometimes we forget when we're doing our lab reports. But we had a mixture of iron, salt, and sand in the evaporating dish. We took the iron out with the magnet. We decanted and poured off the saltwater solution. So we were simply left with wet sand in the evaporating dish. And we knew the mass of the evaporating dish to start because you determined that. And after we heated it up a bunch of times to remove all of the sand, this little box right here, we heated it up multiple times because we wanted to make sure all the water was gone. So once we got two results that are close to one another, well, we know that the sand is completely dry. This is called heating to constant mass. So after we did that, after we heated up the sand for the third time, you may have only had to do it twice, but after the third heating, it was 31.23 grams. So originally, the evaporating dish had a mass of 30.44 grams, and with just the sand in it, after everything else was removed, the water, the salt, and the iron, it went up to 31.23 grams. So to get the mass of just the sand, all we have to do is, again, get a difference. Pretty straightforward. So you subtract those two numbers, the mass of the sand is 0.79 grams. So there's a lot of just subtraction in this lab. But again, when you're looking at a big list of data, you could get a little confused. So we put the mass of the sand in, 0.79 grams. What's the percent? Sand by mass of the percent, mass of the sand by mass. So all you got to do is get the mass of the sand divided by the mass of the whole mixture. And we know the mass of the mixture, it's 2.50 grams. We just calculated the mass of the sand. We just simply take 0.79 grams divided by 2.50, multiply it by 100 to turn it into a percent, and we end up with 31.6%. Just as an FYI, notice that this number has 2 sig figs. This number has 3. That decimal is significant because scientists are lazy. Remember, that's the rule. We wouldn't add a 0 in if we didn't need to. Why would I write that if it only had 2? But this one only has 2, so I am going to round this number. This is kind of one where I would let you get away with it if you gave me 3, but technically we want to turn that to 32%. And remember, this doesn't really count in our sig fig calculation, so because that's just a known number, turning it to 100. So 32% by mass, the sand. How do we figure the mass of the salt? Well, we poured our salt water off into a beaker. I believe you used a 50 milliliter beaker, but this is the only picture I could find. And we poured it in here, and we knew the mass of this system to start, right? Mass of the 50 milliliter beaker in the watch glass, 38.27. And you had a bunch of salt and water in there, and you basically heated that up until all the water was gone, and you were just left with salt. So we're going to do the same exact thing. The beaker and watch glass, and the data I give you here, had a mass of 38.27. And then the one with the salt in it, after we heated up the salt water in it, after we poured the salt water in several times and heated it, the mass went up to 38.83 grams. Again, we're doing the same exact thing. We're just getting a difference. So when you subtract these two numbers, the mass of the salt is 0.56 grams. And obviously the next step is the percent salt by mass. We put that number in. Again, same thing. We're just going to do mass of the salt divided by the mass of the total mixture. 0.56 grams divided by 2.50 grams times 100 is 22.4%. And I am, because of the sig fig rules, going to be technical and round this again. 22%. And just as a check of error, I believe I asked you a few questions at the end. Does each individual percent add up close to 100? Well, with this data I made up, of course it's gonna, because I wanted to, use realistic or accurate data anyway. So sand was 32%, salt was 22%, iron 44.8. You add them up, they're about 99%. So if I didn't give you perfect data, I left room for a little bit of error. This would be some very careful and accurate measurements. And another test, you can add up your individual masses. Do they add up to the mixture? Because we knew the mixture was 2.50 grams. We might have lost some salt or some sand in the process in the rest of our steps. So if our numbers add up very close to this, then we knew we were very careful. We know we didn't really lose anything in the process. So in this case, if you add up these three masses, they do come very close to it, 0.03 of a gram, very, very minimal amount. In fact, on the balances that we have, you can blow on them, or a light wind can change the scale by that much. So this is a very good set of data, and again, I made it up. But you should be able to get good data if you measure carefully in this lab. So that's how you do your calculations. on your separation of a mixture lab. This is Mr. Spohn. I'm out.